iso mean same and the top mean places. So the atom of the same element having the same proton number but the different neutron number, they are represented in the periodic table on the same places. So that's why they are called isotopes. Now we have the three different isotopes of the hydrogen atoms. So we can see that the numbers of the proton and the nucleus of a hydrogen atom, these are the same. For example, the number of the proton in the first isotope is a 1, and the second is also 1, and in the third is a similar situations. If you're gonna see that the number of the neutrons, so these number of the neutron in the different isotopes are the different. For example, in the second isotope, there's a 1 neutron. In the third, there are 2, while in the first one, there is a 0. So the all isotope have same number of proton, but the different number of neutrons. So they have the different atomic masses. So we defined the atom of the same element having the same atomic number, but the different atomic masses are called isotope. Now, if you see that the number of the proton are same and the number of the electron are also same. So if they have the same number of the electron, so their chemical property is the same and their physical property, like the boiling point and the melting point and the freezing point, will be different. So now there's a question, how to calculate the individual isotope masses. And to calculate these masses, we are using mass spectrometer. Now this mass spectrometer calculate the isotopic masses. So for example, if you have the 3 different isotopes in the hydrogen, so the mass spectrometer can calculate the individual isotopic masses. And by finding these relative abundance of isotope in an element, we can calculate relative atomic mass. Now, this relative atomic mass is basically average mass of isotope, which is compared with carbon isotope number 12. So, relative atomic mass is represented in the form of average atomic mass on the periodic table. So we're going to overlook about the mass spectrometer. Now this mass spectrometer is an instrument which is measuring the mass of the different isotope belongs to the same element, and it represents these relative percentage with the help of a mass spectrometer graph. So this mass spectrometer consists of the different parts. For example, the first part is the vaporization chamber. Now this vaporization chamber separates the different molecules by heating. If you are using the gases, they're already separate. But if you're using the liquid or solidified substance, so these molecules are separated by the process vaporizations. And this vaporization chamber is connected with ionization chamber. This ionization chamber contains strong electric field, and this strong electric field passes the electron from these molecules and convert them into the ions. And next is the accelerator, and this accelerator, the speed up the dispersed ion into a beam shape. And this accelerator is connected with the deflection chamber, which contains magnetic field. Now this magnetic field contains strong magnetic lines. And these strong magnetic line of force separate the different ions on the base of their mass to charge value. And these different ions, so they have belongs to the different isotopes. So as we know, these different isotopes, they have the same charges, but the different masses. And on the base of these mass to charge value, these are separated in the magnetic field. And after magnetic field, we have collector. This collector collect these different isotopes on the different position and represent them in the form of their relative abundance in mass spectrometer graph. We're going to see the working of a mass spectrometer. For example, if we have one sample of the gas chlorine, and we want to know what are the different type of isotope present in the chlorine gas. So first, in a vaporization chamber, we will vaporize this chlorine gas, which is already in a gaseous state. And this will have the different type of isotope. For example, the chlorine, one isotope is 37 and another is 35. Now, these different isotopes, when they transfer to the ionization chamber, so in a high electric field passes the electron from these molecules, and these strong electron will knock out the electron from their outmost shell, and they get one same positive charge. Now, these electron, when they passes from there, and they will convert the molecule into different ions. Now, these ions will transfer to the acceleration chamber. This acceleration chamber will convert the scattered electron into one single beam and transfer it to the magnetic field. So when the strong beam of electron will pass from the magnetic field, it will get separate on the base of their mass to charge value. For example, so all will have the same charge, but they have the different masses. So which have the low mass, it will be attracted more toward the magnetic field, and they will get separate from each other. What about the some molecules will left over also in the ionization chamber, and they will not affect the collector? Now you can see that there are the two isotopes present in the chlorine gas, and these isotopes contain the same charge but the different masses. Now on the basis of their mass to charge value, they get separate in the magnetic field, and they got the separate position in the collector, and this collector will transfer them into their relative abundance and show the relative percentage in the given sample. For example, the percentage of the chlorine 35 will be with the 75%, while the chlorine 37 will be 25%. Now we can calculate their average atomic masses by multiplying their mass to their percentage of one isotope to the mass and percentage of a second isotope over 100. So we're going to see how to calculate this mass spectrometer value into the average atomic masses. So here we're going to calculate the relative atomic masses. Now these relative atomic mass can be calculated with the help of this formula, the mass of one isotope multiplied to the relative abundance plus mass of second isotope multiplied to their relative abundance divided by 100. So we calculated the chlorine gas contain two isotopes. One is the 35 and second is the 37. So their percentage, the 35 multiplied their 75, the percentage abundance, and 37 multiplied 25. We can also represent this formula in the form of percentage abundance. For example, the mass multiplied into the percentage, and mass of second isotope is multiplied into the percentage, and their answer will be 3,550 over 100, and we shall get the relative atomic mass of the chlorine 35.5. So that's our the answer. We're going to do the further more practice on that. So we get data from the mass spectrometer in the form of the graph. Now this graphical data is representing how many different type of isotope present in the given sample. And the second data, so what is their relative abundance, is that, for example, in this graph, we can see 3 different isotopes are present here. So the first isotope is the 20, second is 21, third is 22. While their relative abundance is the isotope number 20 of the neon is 90.9%, while the isotope number 21 of the neon is 0.3%, and the 22 contain 8.8%. So we can calculate these different values so with the help of average atomic mass formula. For example, we're going to take these 3 different isotopes and we collected this data and we shall apply the average atomic mass. So the mass of the one isotope multiplied to their percentage. For example, the 20 multiplied their 90.9 plus 21 multiplied their relative percentage 0.3, 22 multiplied 8.8 over 100. So we shall get average atomic mass 20.179. We can also represent its average mass in the form of the 3-digit numbers or the 4 significant figure according to the instruction of the examiner. For example, the 20.179 can also represent 20.18. We're going to see the second example here. Now we have in this second example, the more number of isotopes are illustrated in the mass spectrograph. Now this mass spectrograph represents how many different types of isotope. For example, the one is on the number 70. The second is on the number 72. The third is on the 73. Now the fourth one on the 74, and the sixth one is 76. And the second type of information, their relative abundance is also available. So we can calculate their relative abundance, and with the help of this given formula, we can calculate this value. So their relative abundance of the germanium is a 70. The first isotope is the 70 atomic mass or isotopic mass multiplied to the 20.6 is percentage. And the second isotope, 72, multiplied to the 27.4 its percentage, and plus 73 into the 7.7 relative percentage. And in the same way, the third, fourth, and fifth, we will 8 divided by 100. So you'll get our value. So I'm going to give you the time. Grab your calculator and calculate your value. If you're slow in calculations, you can also pause the video and you can easily calculate. And at the end, you can compare your answer with. During this calculation, you're supposed to use the scientific calculator. You can also calculate individually, or you can also calculate together these all values, and you will get your one answer. So if your answer is correct, so mark will be divided to your answer and your procedure. Now in this way, we got this, the average atomic mass is the 72.703. Now, if you need the 4-digit number, or if you need the 4 significant figure, so that will become the 72.70. So that will be the average value. We can also represent in this way. We're going to move to the next question here. And in this next question, a sample of rubidium was analyzed in a mass spectrometer to produce the mass spectrum below. Now in this question, examiner has given us the graph, mass spectral graph, and asking to calculate the relative atomic masses of this rubidium sample and give your answer to the three significant figure. Now, if you see that in this mass spectrograph, we can have the two different isotopes and their percentage has been mentioned. So we are supposed to take our scale, make a line with the y-axis to their percentage, and we can identify the relative abundance. For example, the percentage I perceive the isotope number 85 atomic mass contain 71, while the relative isotopic mass of the 87, they contain 29. You can also perceive like some student they perceive the 72 or some student they perceive the 28. So it will work. Why? Because this type of question, examiner will give you a big range for the calculations. So the mass spectrometer graph of this rubidium, that is the isotope number 85 contains 71%, and isotope number 87 contains 29%. So with the help of this formula, we can calculate this value. So please grab your calculator, apply this formula of relative atomic mass number, and you can calculate their relative atomic masses of rubidium. You can also pause this video and calculate at your own pace. We're going to check the answers that's relevant. The relative atomic mass of the rubidium is the 85 multiplied to the 71% plus 87 multiplied to the 29% over 100. So the relative atomic mass will be 85.56. Now that is the three significant figure. If you want to represent that will become the 85.6 in an average value. Find your answer if you feel the discrepancy of your calculation and my answer, so you can recalculate once again. There is might possible by using of the scientific calculator. If you put some value, the different, or some signs are the different. So that's why when you will calculate the second time, it might possible the accuracy and precisions will increase. We're going to move to the next question here. The relative atomic mass of hydrogen is represented in the periodic table is 1. So this is correct to the two significant figure. So the table gives the data for the relative isotope mass and the natural abundance of the two stable isotope of hydrogens. So as we studied, like hydrogen contain the 3 isotopes, but in this table, the examiner has given us the stable isotope of hydrogen. Now hydrogen, the isotopic number 1.007825, while the percentage is 99.9885. So calculate the relative atomic mass of hydrogen from this data. So we shall apply the similar formula, and by using the scientific calculator, so we can calculate this value easily. The relative atomic mass is a 1.007825 multiplied to its percentage abundance 99.9885 plus the second isotope, that is a 2.014101 multiply 0.0115 divided by 100. So you can calculate at your own pace. You can also pause the video and you can calculate at your own pace. Now here, sometimes the student, they don't take the other figure and they calculate the few figures. So in this way, I will advise you so to calculate all these number even after the point. For example, the 1.007825. We're going to see that the answer of relative atomic mass is the 1.00779. If you're going to make it the average, so we can make it the average is the 1.008. So this answer you can represent. So we have done. We can move to the next question here. A sample of the silicon contain following isotopes. Now there are the three different isotopes of silicons. Isotope number 28 is 81.21%, and isotope number 29 is 14.10%, and the isotope number 30 is 4.69%. So you can apply this formula and calculate your answer. This type of question is a multiple choice question. Examiners asking, what is the relative atomic mass of silicon to the 1 decimal place in this sample? So in this way, the 1 decimal place in this sample, you can get this value. So we're going to apply this formula. So for example, the isotope mass of 28 will multiply with 81.21 plus isotope number 29 multiply with 114.10. And in this way, the 30 will multiply 4.69 over 100. So you can calculate. So in this questions, MCQ's question, there will be rough place available. It will be better to calculate in the rough place. So this will illustrate your examiner, you're working by yourself. So we're gonna see that. So here there's a relative, the atomic mass or that are 28.23. So if you take that to the 1 decimal number, so this will become 28.2. So B is our correct answer here. We're gonna move to the next question here. So Europium atomic number is 63. Now it's used in some television screen to highlight the colors. Now a chemist analyzed a sample of Europium using mass spectrometry. Now results are shown in the table. For example, this Europium, the isotope number 151 is with the relative isotope mass 151, contain abundance 47.77. Now this Europium that contain 153, that relative abundance is 52.23. Now using the table above to calculate the relative atomic mass of the Europium sample, give your answer to the 2 decimal places. So as I advise you, we have to follow the direction of examiner. So if there's a 2 decimal places or 1 decimal places, we have to follow the directions of examination. So here we're going to apply this formula and we're going to calculate the value. So the relative atomic mass of that Europium first isotope 152 multiply to the 47.77% plus 153 multiply 52.23% over 100. You can also pause the video and you can calculate at your own pace. Okay, students, so we got this value. So the relative atomic mass is 152.23. 5, 2, 2, 3. Now here, there will be so many, the different numbers will come. Sometime you got the recurring number. So in this way, you're supposed to follow the direction of the examiner. So now in this, if you follow the direction of examiner, so the correct answer for the 2 marks and 1 mark for error carry forward for the transcriptions and the errors. So in the first provide final answer is a 2 decimal point, and in between 151 and 153. So examiner has given you the range for that. Your answer you can represent 152.5 is an average that will come in between 151 and 153. We're gonna move to the next question right now. So a sample of the magnesiums contain the overall 3 different isotopes, 24, 25, and 23. Sorry, that's a 24, 25, and 26 here. Now, 24 isotope of magnesium with a percentage is 78.60%, while 25 contain 10.11%, and 26 contain 11.29%. So to calculate the relative atomic mass of the sample of the magnesiums, give your answer to the 4 significant figure. Now this magnesiums is basically, they contain the 3 basic isotopes, and most of the chances like this magnesium examiner may give you in the mass spectrometric graphic value, so the relative abundance will be given in the mass spectrometric graphic value. So we're going to calculate this magnesium relative atomic masses. So you are supposed to use this formula and calculate this value. Now you can calculate by yourself the step number 1 and the step number 2. After calculation of these previous questions, I'm expecting from you, you will be pretty sure about this concept, and you can easily calculate. If you want to calculate at your own pace, you can pause this video, and at the end, you can compare your answer with. For example, our relative atomic mass is 24 multiplied to the 78.60 plus 25 multiplied to the 10.11, and the third 26 multiplied 11.29 over 100, we shall get the average atomic mass is 24.3269. So that for significant figure, we can represent our answer, the 24.33. So here there's like the 2 marks for the correct answer, 24.33 with no working out. For example, that's very much pretty sure if this question is coming in your manuscript exam, written exam. So you are supposed to write your step number 1 and step number 2. Now for their step number 1, you're supposed to calculate these values. So, and their calculation method should be properly illustrated. So it will be more appreciable. You convert this step number 1 into the 2 further steps that will be more easy for your examiner to identify your method. So these 2 steps will be enough. So that's the for procedure, you can have the 2 marks, while for the correct answer, you can have the 2 marks. We're going to move to the next component, that end of our mass spectrometer. So in this mass spectrometer, we calculated the different isotopic masses of the different isotope present in one element. So this mass spectrometer we studied, it consists of the different chambers like vaporization chamber. It evaporate or vaporize the different samples into the gaseous state in which the different molecules get separate from each other. And next is the ionization chamber, so which ionizes these molecules, but some molecules they left over. And after that, we have acceleration. So it speed up the ionic beams, which are scattered. What about the magnetic field? Separate them on the base of their mass to charge value. And the collector collect these the isotope on the different location and convert them into their relative abundance and represent on the mass spectrograph. And we can calculate the average atomic mass data with the help of this given value. Hope you got idea about that, and I hope so it will be valuable for you. Thank you. Thank you very much for staying.